Let's say we start with this vector x. Okay. Now we're going to decompose this, factorize this vector x into two parts. One is the distribution part. Okay. So the normalization must be done because efficiency or magnitude does not matter. You basically look at this vector and divide each entry by the summation of all the entrants. Okay, so this normalizes the whole vector, and each entrance is now between 0 and 1. And then you look at the thing that you use to normalize the vector. That's the summation of the values of the entrants, sum xi from 1 to n. So this part is the distribution part, this part is the efficiency part, and we care about both. So how about we use, well, our fairness function f sub beta to act on the normalized vector, mapping that vector to a scalar, talking only about the fairness of a distribution. And then let's look at the measure of efficiency, let's say by using the same utility function, okay, u sub beta, okay, acting but this time on a scalar. The scalar is namely the summation of all the resources. Okay, it's not acting on a vector, it's not acting on a scalar, but that's fine. Okay, where's my alpha fair utility function? Well, here's the alpha fair utility function. U sub alpha of x, whether this is a scalar or vector. Okay, scalar is just 1 minus x to the power minus alpha over 1 minus alpha. All right, so now we got a measure of efficiency through this function, and then we got a measure of distribution fairness through our f function. Now if you put the two together, meaning you multiply the two, okay, turns out adding doesn't work, but multiplying works. Okay, you basically provide a lift to the fairness value by the efficiency measure here. Then this gives you nothing but the alpha fair utility function acting on the entire vector x, where beta is just alpha, another name for alpha. Okay. In fact, it's precisely because alpha is already used in the alpha fair utility function that we decided to pick the symbol beta to parameterize our fairness function. But in the range of 0 to infinity, let alpha be beta. And it turns out that alpha fair utility acting on the vector x can be decomposed or factorized into two multiplicative components. The first only cares about distribution, the other only cares about efficiency. Okay, so inspired by this factorization that you can easily verify yourself, we now want to construct what we call a welfare function that cares about both fairness and efficiency. Okay, so I care about fairness. Okay, and if this x is not already normalized, by sticking into this function, it will be normalized. Okay, and I care about efficiency, the summation of xi. Okay. Now let's say I want to weigh the fairness part by lambda. Okay. Now we know that it's not the sum between the two components that will show up. We instead want to talk about the product. Okay, but a times b can also be represented in the dB scale, in the log scale, as log A plus log B. Okay, so let's take the log of this and then add the log of this. In fact, to be more precise, we're really talking about the log of the absolute value of this, because this function could be actually returning a negative number, and then put the sign of that in front. But let's skip that part of the complexity here. Okay, just say that it's basically a weighted sum of the log of a fairness component and log of the efficiency component, where the weight of this weighted sum is a number lambda. So in addition to beta, which is some number between minus infinity and infinity, which describes the shape of your fairness notion, there's now also another parameter lambda, which is between 0 and infinity now, giving a relative weight to fairness of distribution relative to efficiency of the distribution. Okay, so this is the function that we are going to look at. We call that a phi, okay, as a function of x. So clearly phi depends on what lambda you pick. Well, how do I compare two vectors under phi? Well, I can look at whether phi of vector y is bigger than or equal to phi of vector x. Okay. Now here comes something that is very non-controversial. Okay. Different people have different notions of fairness, but most people would say that, look, this point and this point, these 2 points are easy to compare. Okay. This point and these 2 points might be hard to compare, but these two are easy to compare because this point, say call it y, this point x, this one strictly dominates this one. Okay, in both x's, say two classes of users, you actually get more for both classes if you go from this point to that point. And this is the notion of a Pareto dominance. Just like back in lecture 1, so this is actually a good lecture to wrap up. We saw quite a few ideas we encountered in previous lectures, all the way back to lecture 1 on Pareto efficiency or Pareto optimality. Now, a similar concept. It says that even in high dimensions, sometimes you have a clear ordering of points. Okay, this point is clearly better than that point. Okay, because all components of this point is better than or equal to another component. Okay. In that case, we say y Pareto dominates x. So we say y got to be a better point than x. Now the question is, if y Pareto dominates x, does that imply or not, that's the question mark, that our welfare function captures the ordering between x and y? Will phi acting on y be greater than or equal to phi acting on x? A similar spirit as the definition of shear concavity for functions. If this implication is true, then we are happy. If it's not true, then we're not happy. Okay? Because even when y dominates x, somehow y is viewed as a worse point than x according to our welfare function. There's a problem with our welfare function there. Well, but if you think about it, that could happen, right? Our welfare function gives a weight lambda to the fairness component. If I make lambda really big, okay, eventually the fairness part will dominate, and it will say, look, this is exactly on the 45-degree line. This is just a little bit off. Okay, and therefore x is better than y, even though it's dominated by y. This is all the way back to the beginning of this lecture when we talked about the choice between everybody starving to death together versus everybody becomes a billionaire, but one guy got another dollar more. Okay. So clearly, if we put too much emphasis on fairness part, if lambda is too big, this will not hold. So we have to say lambda cannot be too big. Lambda has to be less than or equal to some threshold in order for this to hold. And it turns out that the threshold is beta over 1 minus beta absolute value. Okay, so skipping the derivation, we say that if lambda is less than or equal to this value, then we guarantee this implication relationship holds. In other words, our welfare function is of one that makes sense. Okay, it makes common sense. All right, let's say we let lambda go all the way to be exactly this, not just less than or equal to, but hit this upper bar, okay? And then substitute the resulting expression to phi and see what kind of function do we get. And lo and behold, the function that you get from phi now is nothing but alpha fair utility function. In other words, actually alpha fair utility function is an extremal case that says, put as much emphasis on fairness as you can without breaking the common sense condition. Then the welfare function, a generic function, this one, reduces to the special case, which is the well-known isoelastic or alpha fair utility function. So that entire derivation is hidden from the definition of alpha fair or isoelastic function. But now we dig that up. So you can pick an alpha or a beta that defines the shape of your fairness function. And then I can tell you accordingly there's a maximum emphasis lambda that you can put on the fairness component relative to the efficiency component. And if you exactly go to that extreme, then you recover alpha fair utility function. And this is why we say bigger alpha is more fair, because alpha fair utility function is really an extremal point in the space of social welfare functions. So now we have a new unification. Suppose out of those 5 axioms, we take away one of them and bring it down to 4 axioms. Which one do we take away? The axiom of homogeneity that says this function acting on vector x is the same as this function acting on 5 times this vector s. Okay, or 10 times, or 0.1 times. The scaling doesn't matter. If we strike that axiom away, and then we're left with the other 4 axioms, and then see what happens. Skipping the detail, it turns out that what we'll see is that there's a unique family of function that can satisfy the new set of 4 axioms. We represent that by big F, because letter F is already used in our own notation. Big F, which is parameterized by beta and lambda, acting on vector x. And that turns out to be, okay, it just by coincidence turns out to be the product of the original fairness function. If you still recall what that looked like, I don't want to write it again. This function, this is the original function, okay, where efficiency is not part of the story. It equals to that function times the summation of xi. Now finally efficiency comes into play, raised to the power of 1 over lambda. Now this 1 over lambda is also called the degree of homogeneity. Okay. I guess of homogeneity of this function. Okay. So I'm skipping 2 things. A, I'm skipping the set of 4 axioms, and B, I'm skipping the derivation that says there's actually a unique family of function that can satisfy all the 4 axioms, which so happens to be expressible in this kind of form. That rings a bell, since this is what we already have seen, and this is a component that also looks familiar given the discussion we just had about alpha fair utility function. But I want to highlight, actually this is derived just from the 4 axioms. Okay. So now we have this function that incorporates both fairness, whose shape is parameterized by beta, and efficiency, whose relative weight with respect to fairness is 1 over lambda. And we know this is the only family of function that can satisfy those 4 axioms. And it turns out it unifies many diverse set of functions in different fields, including Jing's index, Jessel index, Tail index, Atkinson index, Shannon entropy, Rennie entropy, alpha fairness, Foster-Sun function, p-norm, and the list goes on and on. Okay, so you can look at the textbook for a collection of those. So somehow this function, I didn't write this out in detail, but you can substitute that in. Somehow this function, asymmetrically constructed, captures a lot of fairness measures that can map the entire vector into a single scalar for comparison. Now let's go into 2 examples to illustrate the use of this unified notion of fairness and efficiency.